Okay, so hello and welcome back. So in this video we want to talk a little bit about algebra of real functions. So the text is, there is not much material here left, and of course we are going to need the algebra of these real functions for the next part of functions that we have in class 12. So let's get started on this. So about algebra of real functions. Basically what we have is that in this section we shall learn how to add two real functions, subtract a real function from another, multiply a real function by a scalar, and scalar here is meant by, what is meant by a scalar is a real number, and multiply two real functions and divide one real function by another. So we want to do a couple of things. So first we shall learn how to add two real functions. And then we will learn how to subtract a real function from another. How to subtract a real function from another. Then we will learn how to multiply a real function by a scalar. Multiply a real function by a scalar. Then we will learn multiply two real functions by a and then we will learn how to divide one real function by another. That's basically what we will learn here. So the first thing that we will do is basically addition of two real functions. Addition of two real functions. So in this section we shall learn how to add two real functions. So addition of two real functions. Let f be a function. Let f be a function from x to r, and g be a function, from x to r. Be any two real functions. Be any two real functions. And you know that and when we say a real function, as you know, what we mean is that if the range of the function is the set of real numbers or some subset of that. Now this definition is has a couple of problems. It's not properly defined, but since we don't have a better definition for now, we will have to go with this definition for now. So until we get a better definition. So when we say, at least for now, what we mean by a real function is what we mean. There are basically two terms that we had. First of all, we had the real valued function. The real valued function. And we had also the real function. Now, the real valued function is the function in which the range of the function is the set of real numbers or some subset of that. Again, as I mentioned, the definition is not very much defined, but it's better than nothing, really. And a real function is a function in which basically, in addition to the range of the function being the set of real numbers or some subset of that, in addition to that, the domain of the function is also the set of real numbers or some subset of the set of real numbers. That sort of function is called a real valued function. Okay. Okay, so now what we have is, let f be a function from x to r and g a function from x to r be two real functions where x is a subset of r. Where x is a subset of r. So basically x is a subset of r, and meaning that the domains of the two functions are subsets of the set of real numbers, and the codomains of the two functions are, well, the real numbers, the set of real numbers itself. So, and based on the same reasoning, you can call the two functions two real functions, right? Then we define f plus g . Then we define f plus g of x as, f plus g is as a function from x to r, by f plus g of x is equal to f of x plus g of x for all x belonging to x. So pretty simple definition. I have no basic, I suppose everything is pretty simple about this. Now about subtraction of a real function from another. Number 2, about subtraction of a real function from another. So about subtraction of a real function from another, basically you can say that let f be a function from x to r, and g be a function from x to r. So let these be any two real functions. Where x is a subset of r. Then we define f minus g then we define f minus g then we define f minus g as a function from x to r by basically f minus g of x, f minus g of x is equal to f of x minus g of x for all x belonging to x. That is the subtraction of basically a real function from another real function. Number 3 is basically multiplication by scalar. Number 3 is basically multiplication by a scalar. So about the multiplication by a scalar, so we have let f be a function from x to r. Let f be a function from x to r. Be a real valued function. Be a real valued. So you can notice that here this is a real valued function. Meaning that the domain of the function is not necessarily the set R or any subset of the set of the real numbers. And alpha be scalar. And alpha be a scalar. Here by scalar we mean a real number. Then the product alpha f is a function from x to r. Then the product alpha f is a function from x to r. Is a function from x to r. Defined by alpha f of x is equal to alpha times f of x for basically x belonging to x. And about multiplication of two real functions, number 4, about multiplication of two real functions. So about that, the product or multiplication of two real functions the product or multiplication of two real functions f from x to r, f from x to r, and g from x to r is a function fg from x to r the function fg from x to r defined by fg of x is equal to f of x times g of x for all x belonging to x. This is also called pointwise multiplication. Pointwise multiplication. We call it also pointwise multiplication. So that means that when you do the multiplication of two real functions, that is also called pointwise multiplication. And basically part 5 of this is called quotient of two real functions. Quotient of two real functions. And about the quotient of two real functions, you can say that the product, or let f and g be two real functions. Let f and g be two real functions. Defined from x to r. Defined from x to r, where x is a subset of r. The quotient of f by g denoted by f by g is a function defined by f by g of x is equal to f of x divided by g of x, provided that g of x is not equal to 0. Provided that g of x is not equal to 0 and x belongs to x. So now let's do a couple of examples here. Example number 16. We have let f of x is equal to x squared and g of x is equal to 2x plus 1. Be two real functions. We want to find basically f plus g of x, f minus g of x, f times g of x, and f divided by g of x. We want to find these things here, and this is example number 16. Okay, so as the solution we have basically, so first of all, if you want to find basically f plus g of x, that is equal to f of x plus g of x, right? So f of x plus g of x is going to be x squared plus 2x plus 1, and that is basically f of x plus g of x. Now f minus g of x is equal to f of x minus g of x, which is equal to x squared minus 2x plus 1, which is equal to x squared minus 2x minus 1. Now f times g of x is equal to f of x times g of x, which is equal to x squared times 2x plus 1, which is equal to 2 times x cubed plus x squared. And f by g of x is equal to f of x divided by g of x, which is equal to basically x squared divided by 2x plus 1, of course provided that basically 2x plus 1 is not equal to 0, and so that means that 2x is not equal to negative 1, which means that x is not equal to negative 1 by 2. So that is example number 16. Now example number 17. Okay, so example number 17, we have let f of x be equal to the square root of x, and g of x be equal to x, be two functions defined over, let these two be two functions defined over the set of non-negative real numbers, over the set of non-negative real numbers, meaning that x belongs to the set of R plus, I think they write it this way. So then you want to find f plus g of x, f minus g of x, f times g of x, and f divided by g of x. Now we have basically f plus g of x is equal to f of x plus g of x, which is equal to the square root of x plus x, and f minus g of x is equal to f of x minus g of x, which is equal to the square root of x minus x, and f times g of x is equal to f of x times g of x, which is equal to the square root of x times x which is equal to x raised to the power 1 by 2 times x raised to the power 1, which is equal to x raised to the power 1 by 2 plus 1, which is equal to x raised to the power 3 by 2. And f divided by g of x is equal to basically f of x over g of x, which is equal to the square root of x over x. Of course, you can write this as x raised to the power 1 by 2 times x raised to the power, or you can say divided by x raised to the power 1, which is the same thing as x raised to the power 1 by 2 times x raised to the power negative 1, which is the same thing as x raised to the power 1 by 2 times x raised to the power negative 2 by 2, which is the same thing as x raised to the power 1 by 2 minus 2 by 2, which is equal to x raised to the power negative 1 by 2, which you can write as 1 over, for example, x raised to the power 1 by 2, which is equal to 1 over square root of x. That way you can write it as well. And this is, of course, provided that x is not equal to 0. Because if x is equal to 0, then your denominator goes to 0. And then we have